So now we'll cover the chi-squared tests. Okay, so this is a chi. It looks like an X, but it's the Greek X, and it's the chi-squared test, and it's a this isn't mathematical statistics, but it's the distribution of basically a normally distributed, or like a standard normal variable that has been squared. So so it looks the distribution itself, not that this really matters, but it looks kind of like this. Okay, this is what a chi-squared distribution looks like. But anyway, okay, so we have the goodness of fit test. Okay, goodness of fit test, and the question here basically is, we have, the setup is we have one categorical variable with and so the observations can belong to one of however many categories we have. So maybe we have 4 different categories or something like that. Okay, so we have one categorical variable, and we have proportions in mind for each of those categories. For each category. And the question is, how well do these proportions fit the data that we observed? Okay. Okay, so maybe, or like, how good is the fit, okay, between the proportions and the data? And so, so here's an example. Okay, maybe you want to see, does a die roll fair? Okay. So you have 6 categories, you have basically 1, 2, 3, 4, 5, and 6, and we are expecting the proportion to be 1/6, 1/6, 1/6 for all of these. Okay, so 6 categories, we expect each face to show 1/6 of the time. Okay, or does a die roll fair? Or perhaps maybe you have some kind of, what are these called? Punnett squares for like genes. And you have like A and A little a, and you got, yeah, that's what it's called, right? Huh? The Punnett square, something like that, right? Okay, and then so so if this is, did I even do this right? I think. Okay, so we expect this is so that we have 3 categories here. Okay, we have AA, and then A little a, and little a, so we have 3 categories. And then kind of the proportion, we expect to show up something like 0.25, 0.5, and 0.25, right? Something like that. Okay, so so these would be examples where we could use the chi-square goodness of fit test. Okay, so you know, I mean, this could be like I don't know, you're crossing some kind of like flowers or something, and maybe this corresponds to kind of the flower is red, and this is the flower is white, and then here the flower is pink, or something like that. You know, I don't know, something like that, right? So, huh?
That's right.
That's like the classic example or something that I'm just making up, sort of. I think like I kind of remember this from like my 9th grade biology or something. You know, like this is about my knowledge of this goes. Okay, so so you know, we have something like this, and we want to know. Okay, so let's say this is like the genetic model, right? So under the genetic model, you're expecting these proportions to show, and then you go out, and maybe you go out and you collect a random sample of flowers, and you go, okay, well, let's see how well do our flowers actually fit this genetic model, right? So we might ask this question, right? So this is the hypothesized genetic model. Okay, and then you know, we gather data. Okay, so let's say we red flowers, so that would be under the genetic model. Let's say we have 52 of them, and then pink flowers, we get, I don't know, 90 of them, and then white flowers, we have, I don't know, 60. Okay. So let's say this is what we observed. This is a random sample. Okay, and so the question now is, do our data fit the hypothesized proportions, or is this different from this to now for us to doubt this model? That's what we want to know. Okay, so this is the situation where we use the goodness of fit test. We got one categorical variable. In this case, it's the color of the flower. We have proportions in mind for each category, and we want to know how well do these proportions fit the data we observed. Okay. All right. So we'll stick with this this example here. And so for the chi-squared, this is the goodness of fit test. Okay. Our null hypothesis will be the population consists of the following proportions. Consists of the proportions being probability of red equals 0.25, probability of pink is 0.5, and probability of white is equal to 0.25. Okay? And the alternative hypothesis is at least one of these proposed proportions is wrong. Okay. Now, anytime you have more than two categories, the alternative will always be non-directional. So if you have over two categories, alternative is always non-directional. Okay. If you have only two categories, you could have a directional alternative, because what it boils down to is that if you've got too much of category 1, then that means you don't have enough of category 2. But if you have more than two categories, like if you have 3 categories, let's say it turns out the data shows that there's too many white flowers, okay? Well, then that means maybe we have too few red, or we have too few pink, or we have too few of both, and it doesn't really specify. If you're observing too many of one category, it doesn't specify where you should be taking from the other, because everything has to add up to 1, but when you have more than 2, it's not, the test results won't tell you which one is which. So the goodness of fit test, when you reject the null, it's just going to come to the conclusion that at least one of the proportions is wrong, and it won't actually tell you which one it is. You can look at the data and kind of suspect which one it is, but the test itself won't tell you that. Okay. So here are our data. I already forgot what I wrote on the previous slide. I had red, pink, and white, and 52, 90, and 60. Okay? So this is what we observed. Okay? And so what we're going to do is we're going to compare kind of the reality versus the expectation. Okay? So we're going to compare what we observed versus what we expected. Okay? Okay, and so what we do is we say, okay, well, how many plants or flowers do we observe in total? So we'd say 52 plus 90 plus 60. I observed a total of 202 flowers. Okay, so under the expectation, if these proportions were exactly correct, I would expect red to be 202 times 0.25. I would expect to get 50.5 red flowers. Pink flowers would be 202 times 0.5, and that would be 101 pink flowers. And white flowers, I would also expect 50.5 white flowers. Okay? And it's okay to have decimals here, all right? Because these are expected values. Okay? In your observed values, of course, you're only going to have whole numbers because you can't have you can't get a half flower or something like that. Okay? And so, but for expected counts, it's okay to have decimals. Okay? So you just do basically n times p for each category. To get the expected count. Okay, and decimal values are fine. So don't like round these off. Okay. All right, and then the chi-squared statistic is what we're going to do is we're going to take the observed minus the expected, and we're going to take the squared difference between these, and we're going to divide that by the expected. Okay, so it's observed minus expected divided by the expected. Okay, and we're going to add them up for all categories. Okay. So in our case, the chi-squared statistic is we're going to do 52 minus 50.5. This is what we we take that difference and we square that difference and we divide by 50.5. Then I do the next. I observed 90 pink flowers. I'm expecting 101. Square that difference divided by what we expected. And as far as white flowers go, I observed 60. Take off the expected, we square that and divide by the expected. Okay, and we're going to add these up and we're going to get a chi-squared statistic, a test statistic value here. Okay. So this is just mashing the calculator. Whoops. Okay, 52 minus 50.5 squared divided by 50.5 plus 90 minus 101 squared divided by 101 plus 60 minus 50.5 squared divided by 50.5. Okay, I'm getting a test statistic of 3.03, 3.0297. Okay, I don't know if anyone's going to bother trying to verify this, but but this is what I got here. Okay. Okay, so we're just comparing, you know, what we observed versus what we expected. Okay, that's kind of the comparison. And you know, if they're super different, then that would give an indication that our proportions are wrong. And if they're not super different, then maybe our proportions are, the proportions could be right. It doesn't prove that they're right, but they could be right. Okay, so at this point we're going to take this and look this up in a chi-squared table. Okay, we have a reference table, and so my chi-squared statistic is 3.0297. We're good? Okay, so we got chi-squared is 3.0297, okay? And we're going to go to the chi-squared table. Okay, so the chi-squared table also has a degrees of freedom term, and here it's the number of categories minus 1. So here I have 3 categories, red, pink, and white, and so I have 2 degrees of freedom. Okay, I go to the chi-squared table and I'm going to look up with 2 degrees of freedom where 3.0297 falls, and we see that it is greater than, it is less than 3.22. So in our table we have at 2 degrees of freedom, the first number that shows up is 3.22, and that corresponds to a tail area of 20%. And the next number is 4.61. That corresponds to 10%. So 3.02 or 3.03 falls right here. And so that means my tail area is going to be greater than 20%. Okay. So far so good? Okay. All right, and so everything here, these are column headings are for non-directional p-values, which is what we have. Okay, and it even says if the alternative is directional, which is only possible when degrees of freedom is equal to 1, you'd have to divide the tail probability. So here our p-value, we have a non-directional alternative, so our p-value is greater than 20%. All right, so what does this mean? So this means that, you know, I'm expecting 50, 101, 50.5 here. I only got 52, and I only observed 90 pink flowers and 60 white flowers, but that, as far as the data goes, is not an indication that that my proposed proportions are wrong. Okay, this the fact that this was what I observed is not evidence that the null hypothesis is wrong. It doesn't prove that the null hypothesis is true, but it is not evidence that it's wrong. So here we would say our p-value, let's say, assuming alpha is 0.05, we would have our p-value is greater than alpha, so we do not reject the null hypothesis, okay? And we would say we do not have evidence that the proportions of different colored flowers, or the proportions of different, colored flowers under the genetic model are wrong. We cannot say that this proves that the genetic model is correct, okay? It's just that we don't have evidence that it's wrong, okay? So do not say that this provides evidence that the model is correct. It's just no evidence to say that it's wrong. Yes?
So it's just to say that that your expected proportions, right? When you're saying the proportions of different colors.
Yeah, your expected proportions. Yeah, so it's just basically we're not rejecting the null hypothesis. The null hypothesis says that the population consists of these proportions. Yeah, all we're saying is that we don't have evidence that these hypothesized proportions are wrong. Okay? Or in other words, that that even when these proportions, even if the population had these proportions, I could get my data that looks like our observed sample just from random chance over 20% of the time. Okay, so data that looks like our sample or something more unusual, as defined by the chi-squared statistic, happens by random chance over 20% of the time. Yes? Yes. Is that good? Okay. Maybe I'll give you guys an example. Just wait for you guys to finish writing. Okay, so maybe we'll say, do we have evidence that we'll just say candidate Y will win over 50% of the popular vote. So this will be our question, okay? So do we have evidence that candidate Y will win over 50% of the popular vote? All right, and then so we took a survey of, I don't know, 250 random people. randomly selected voters. And we will say that 132 said they will vote for candidate Y. Okay? Does this provide evidence? Do we have evidence that candidate Y will win over 50% of the popular vote? So this will be your question. Okay? You can do a chi-squared test to answer this. Okay, so you got to figure out what the categories are, and then what your expected. So to kind of help you out, figure out what your observed values are, figure out what your expected values are, and then do your calculations. Okay. So I'm gonna, if you're watching on YouTube, I'm gonna pause. I would say you should pause the video here because I'm gonna pause it, and then when it resumes, we're gonna go over the answer. Okay, so now I will go over the answer here. All right. Okay, so well, first of all, let's establish our hypotheses. Okay, so we've got a null hypothesis. Okay, and then an alternative hypothesis. Okay, so the null hypothesis, we're gonna have to have proportions for what we think. So we're gonna have to say, you know, basically the proportion of basically vote for Y, and then the proportion for not voting for Y. Okay, because those are our two categories. Either people are gonna vote for Y or not vote for Y. Okay, and under the null hypothesis, we're gonna say that this is 0.5 and 0.5. Okay, and then the alternative is that we want to know if someone's going to win over 50% of the vote. So it's going to be the probability of voting for Y is greater than 0.5, and the probability that not voting for Y will be less than 0.5. So in this case, we have a directional alternative, and that's okay because we only have two categories. So when we say greater than over here, that requires this one to be less than. Okay. Because there's only two categories, if I just write one of these, the other one is implicit. Okay. So basically, I could get away without writing this one, and I could get away without writing this one, and just listing off just one category as well. Okay. Because if we say you're either going to vote for candidate Y or you're not going to vote for candidate Y, then these other values are implicit as well. Okay. Okay. So what we observed is we've got vote for Y, and then we're going to say no for Y. And what we observed is we observed 132 people here, which means if we had a total of 250, we need to have 118 here. Okay. If the null hypothesis were true, we would expect to see 125 here and 125 here. Is that good with everybody? Okay. Yes. Yeah, of course.
So I guess what threw me off is that I guess in the other example, it was like, okay, we have this Punnett square, and we know we would have these theoretically predicted values.
Right.
Whereas here it just is in the form of a question.
Yeah, so it just says, do we have evidence that candidate Y will win over 50% of the popular vote? So it just means kind of the theorized proportions there would be either this candidate gets 50% of the popular vote, or gets more than that. Okay.
So it doesn't have to be like, I guess it doesn't have to be stated as like, we think it will be this, blah, blah, blah. If you just ask, will they win over 50% of the vote, that becomes your expected.
Right. Okay. So will they win over 50% of the vote? That implies I'm thinking that I'm expecting 50%, or and then the alternative would be that it's going to be more than that. Okay. And so again, the null hypothesis always has an equal sign in it. Okay. So you might think maybe I should have a greater, like a less than over here and a greater than over here, okay? Just the way we set up our hypotheses, though, is that the null hypothesis always has an equal sign. So it's either going to be equal to 50% or we have more than that, okay? And so because it's directional, we just want to make sure that directionality is met, okay? So is directionality met? So, I mean, does our data even support the notion that candidate Y gets over 50% of the vote? And when we check, the answer is yes. Directionality is met because in our observed data, candidate Y got over half of the vote, okay? Yes, in our observed data, okay, so that's good, okay? And so so we can continue on with the test, and so we have a chi-squared test, and this is going to have observed minus expected, so we're getting 132 minus 125 squared over the expected over 125 plus 118 minus 125 squared over 125. An interesting thing is that when you have only 1 degree of freedom or only 2 categories, the numerators will always match because they have to add up, right? So you're going to have a positive difference of 7 on the top and a negative difference of 7 on the other side. So you're going to have 7 squared over 125 plus negative 7 squared over 125. So here I get 49 divided by 125 times 2. I get a test statistic of 0.784 and 1 degree of freedom. Okay, so I have 1 degree of freedom. And so looking at here, I see the first value that shows up is 1.64. So all I know is that my tail area is greater than 20% because these are for non-directional alternatives. I would take this and divide by 2. So that just means my resulting p-value is over 10%. Okay? And so we would say, do not reject the null hypothesis. And we say that our data does not provide evidence that candidate Y will get over 50% of the vote. Okay, and so, I mean, and it could be just because our sample was too small, right? We only surveyed 250 voters. It's hard to make conclusive polling decisions based off of a small sample like that. So right now, we have no evidence that candidate Y will get over 50% of the vote. Okay? Yes?
So for this one, the conclusion was based off of the p-value alone. We don't need to compare it to an alpha?
Oh, okay. I'm sorry. So the p-value is greater than 10%. Yeah, we should compare it to alpha. Even if alpha were 10%, our p-value is greater than alpha. So yeah, I'm sorry. My p-value is greater than alpha, you know, whether, you know, if we say alpha is 5% or alpha, even at alpha 10%, our p-value is greater than alpha. And we would say do not reject the null. So we're just looking at 1 degree of freedom there. Okay? Is this okay? All right. The book splits I feel like chapter 10 could just have been tacked on to chapter 9, but the book felt that it should split it out. So so it feels like we're covering a lot today, and we are, to be fair, but the chi-squared test in chapter 10, I think, is really just an extension of this. Okay, so this other test in chapter 10 is called the chi-squared test for independence. Okay, and the key difference between this one and the other one is that the goodness of fit test, there was only one categorical variable, and here we have two categorical variables. We have two categorical variables, and we are testing to see if these two categorical variables, are they independent? Okay. Are the two categorical variables independent? Okay. Do you remember what it means for events to be independent? Yeah, the outcome of one does not influence the outcome of the other. What does this look like in terms of like a probability equation?
It was like, I think it was like when you do probability of A or B, but wasn't it like A given, if it's A given B, something's.
Yeah. Okay.
So
Sure. Okay. Yeah. It is. Yeah. I know. So we'll let me. Okay.
Yeah.
So independent events mean the outcome of one has no influence on the outcome of the other. Okay. I'm sorry. So I'll write all of this out. So the outcome of one event has no influence on the outcome of the other event. Okay, and so we said, as far as equations go, probability of A given B would then be equal to the probability of, if A and B are independent, this would be the probability of A. Okay, so the probability of A, whether B has happened or not, is just the probability of A. Yeah, okay. And then, so this this further influences that when it used to be probability of A and B, this always equals the probability of A times the probability, or I'm sorry, let me say this will be the probability of B times the probability of A given B, okay? But because probability of A given B just becomes probability of A, this becomes the probability of B times the probability of A, okay? Maybe we remember this. It sounds kind of familiar now that I see it up here again. Okay, so we're going to basically use this principle here to get our expected values under if the two variables were independent. Okay, so so you know, we could just say okay, so we'll ask a dumb question here. Okay, so we'll say, is being from California or Texas independent of owning a truck? Okay, all right, and so just playing on stereotypes of what California and Texas looks like, we would say that in Texas you're more likely to own a truck, and in California you're less likely to own a truck. Okay, so this is maybe the sales data don't back this up, but this is just I think it does, and we're gonna just exaggerate this when we make up data for this problem here. Okay, so you know, this is kind of the question we're gonna ask. Okay, and so when we write our hypotheses, the null hypothesis will be that California or Texas is independent of owning a truck, okay? So we'll say California or Texas, being from California or Texas is independent of, truck ownership. Or truck ownership is independent, okay? So to write this symbolically, we would write probability of owning truck given California is equal to the probability of owning a truck given someone coming from Texas, okay? So this is one way to say that they are independent, okay? Do we agree with the way this is written? This says that they are independent, okay? The alternative, we would say, Texas people are more likely to own trucks. Own a truck than California people. Okay, and then so here we would say probability of owning truck, I guess I wrote this backwards, is less if you're from California. Given that you're from California, then probability of owning truck given you are from Texas. Okay, and so this would be a directional alternative. We could, if we just said that it's different, then we would put in a non-equal sign, and it would be non-directional here. So far, so good. Okay. All right. So let's go out and collect data, and we ask people from California. We ask people from Texas. Okay, so we have California, we have Texas, and we have those who have a truck, and we'll say no truck. And I don't know, I'm making up numbers. Okay, so we'll say 30 people and 70 people. Well, I'll say 75, okay? So I have 105, and then maybe we have 55 and 55. So I have a total of 85 people owning trucks. 75 and 55, what is that, 120? Huh? I'm sorry, 130. And so I have 215 people total. Okay, so this is our observed data. Is that okay? Okay, so we're going to create a table of expected values. Okay, so expected counts. And basically, I'm going to just start off by filling in the margins of the table. Okay, so we're going to use the same. Something my computer just read out here. So I'm going to just write the same values here: 85, 130, 215, 110, 105, and this will be California, Texas, truck, and no truck. Okay. And then we're going to say, okay, if the state that you're from and truck ownership is independent, okay? So if truck ownership is independent of, being from California or Texas, okay? what would we expect? Okay, so overall, if I looked at this, I would see 85 divided by 215. What is this number? This is 0.3953. So like a little less than 40% of people overall own trucks. Okay, so truck ownership overall would be 85 over 215. Okay, so we're expecting 0.3953. Okay. If I take this and I apply this, and I would say, well, if truck ownership is independent of which state you're from, then I would expect 39.5% of Californians to own trucks. Okay, I would expect this proportion. So I would take this number and I would multiply it by 105. Does that make sense? And I would say, okay, the number of California people that I expect to own trucks would be 41.51. Okay, so I would take this number and I would say, 105 times basically 85 over 215 gives me 41.51. So, we expect there to be 41.51 truck owners in California. Okay, does that make sense? Mm-hmm. Okay, and so I could apply that and get every other number here. Okay, but there's also kind of there's a thing going on here. This table has what we call only one degree of freedom, in that as soon as I determine this number here, 41.51, all of the other numbers are locked in, because this number plus this number must add up to 85. So I can just do 85 minus 41.51, and that number has to be 43.49. Okay, it has no other choice. Otherwise, it won't add up to 85. And then likewise, I can put this right here, and this has to be 63.49. And I have to do 130 minus that number, and I get 66.51. Okay, so all of these other numbers are just kind of determined as soon as I get that one number. Okay, but I could apply the same rule. Okay, and so one way to get our expected value, so the expected, okay, is equal. We can look at this and we can say, okay, all I did was really just take my column total, 105, and multiply it by 85 over 215, which was 85 is the row total, divided by 215, the grand total. And whether I because the way multiplication and division works, it just works out this, like I could put the denominator, stretch it across both numbers or not. Okay, but basically I'm just saying overall the truck ownership rate is 85 over 215. I'm expecting that same proportion to apply to 105 people from California. And so I'm getting this. Okay, so this is how I get my expected number, right? And then so now at this point I'm going to calculate a chi-squared statistic, which is going to be this exact same as before, observed minus expected squared over expected. Okay, and so here I'm going to have 41 point, I'm sorry, what I observed was 30, and I'm going to subtract off the expected of 41.51. I'm going to square that and divide by 41.51, and we're going to do this for all four of the inner cells. Okay, so I observed 55, I subtract off 43.49, I square that, and I divide by 43.49. Okay, And again, all of these will end up having the same numerator because this table has only 1 degree of freedom. Okay, and that's just one of the nice things that works out. But the denominators are all different. Okay, so and don't forget to do it for all 4 cells. A common mistake I've seen on quizzes is that, I don't know, students will just do like 2 of the cells or something. Okay, that's going to throw off your number by quite a lot. Okay, you're going to have like basically half of the values there. Okay. So, you know, the process isn't too bad, or at least in my opinion, it's not too bad. It's just a tiny bit tedious to type in to your calculator. Okay, and there's not much I can do about that. So actually, let's just do what is? I think it's 11.51, right? Okay, so let's just do 11.51 squared divided by 41.51 plus 11.51 squared divided by 43.49 plus 11.51 squared divided by 63.49 plus 11.51 squared divided by 66.51. Okay, so now I get a chi-squared value of 10.323. 10.323. So this is my chi-squared statistic here. Is that okay? Alright, so let's we'll just copy this in 10.323. I hope I did the math on my calculator correctly. Okay, so we said chi-squared is equal to 10.323. Okay, so the degrees of freedom, when we look this up in the table, it's going to be the number of columns minus 1 times the number of rows minus 1. Okay, so for a 2 by 2 table, it's 2 minus 1 times 2 minus 1, which is you're going to get 1 degree of freedom. So for a 2 by 2 table, it's 1 degree of freedom. If we can expand this to an R by K table or something like that, where you have more rows and more columns, same principle applies. Okay, same. You figure out your expected counts the same way. You figure out the chi-squared statistic the exact same way. It's just a little bit more tedious in terms of now you have like 9 cells to add up or something like that. Okay. Okay, so let's we're going to look up 10.323 in our chi-squared table. Okay, and so we see 10.323 is between the column headings for 0.01 and 0.001. Okay, so our tail area is between 0.01 and 0.001. Okay, these were for a non-directional alternative, and so we have, if our alternative hypothesis was that the probability of a truck given California was less than the probability for truck given Texas. Okay, and we see that if we do California ownership, 30 divided by 105. This is indeed less than 55 over 110. This is, this is 0.5, and 30 over 105 is, I don't know, 28%. Okay, 20.286. Okay, so so our directionality is met. Okay, and so because we have an directional alternative, we would say our p-value is between, and we divide these by 2. So we'd have 0.005 and 0.0005, okay? So this is a pretty small p-value, okay? So we would say, you know, if alpha were, even if alpha were 1% or whatever, okay, our p-value is less than alpha. Okay, and we would say our data provides evidence that people in California are less likely to own trucks than people in Texas. Less likely to own trucks than people in Texas, okay? And so that is the chi-squared test for independence. Are we feeling okay with this process here? Any questions? No, we're good? Okay, well then that's all I've got for today. We'll let you guys off the hook for 8 minutes early. Have a good night.